Thanks. I want to thank the organizers for the chance to be here and to speak. I'm especially grateful to be here at IMPA this morning. And I want to thank Matt Baker, who gave a mini course earlier in the week that covered most of what I discussed in the abstract. And so I'm now free to discuss. Now I'm free to discuss some more recent topics that build on the work that Matt talked about. And everything I'm going to say is based on joint work with David Jensen. So the starting point for Brill-Noether theory for this line of research is to understand curves by understanding how they embed in projective space. And so the basic question that one starts with is, so when does the general curve of genus G embed in PR with degree D? And here we should assume that all of our embeddings are non-degenerate, so not contained in a hyperplane. And the Brill-Noether theorem can be rephrased as answering this question. So we could start with low genus cases. So if we take G equals 0, R equals 1, well, the line embeds in the line with degree 1. And now P1 also embeds in the plane with degree 2 as a smooth quadric. Now a genus 1 curve, we all know all genus 1 curves embed in the plane with degree 3. And if you go up to degree 4, then the genus jumps to 3. So a general curve of genus 3 embeds in P2 with degree 4. And the more precise statement there is that every smooth curve of genus 3 is either hyperelliptic or it's a smooth plane quartic. These are the only cases when the general curve embeds in P1 or P2. And so then we go up to R at least 3, and here we have a nice uniform answer, which is that rho of GRD should be non-negative. And what's this rho of GRD? This is the Brill-Noether number G minus R plus 1 times G minus D plus R. So we have these 4 special cases that I'm going to essentially ignore, and we'll think about the case when R is at least 3. So once we know when the general curve embeds, then we want to know what's the geometry of these embeddings. For instance, what's the geometry of the space of all such embeddings? And this question is a little more open-ended, so we can give several answers here. So one answer comes from the Giesecker-Petri theorem, is that this space is smooth of pure dimension rho. And that smoothness, together with the connectedness theorem of Fulton and Lazarsfeld, tells us that this space is irreducible. When this dimension is at least 1. But then there's still the case when the dimension is 0, and we have finitely many such embeddings on the general curve. And there you might want to think about how this behaves in families. And Eisenbud and Harris tell us that monodromy acts transitively. When rho is 0. So that means, in some sense, you can't distinguish the different embeddings when there are finitely many. And maybe a better way to say this is to take U sitting inside Mg, the Brill-Noether-Petrie general locus. So this is the open subvariety or substack of Mg, parametrizing curves for which the Petrie condition holds. And then we could look at the universal linear series of degree d and rank r over U. And so this maps onto U, and it's smooth and irreducible. So the total space of GRDU is irreducible, and it has relative dimension rho. So because this GRD of U is irreducible, it makes sense to talk about the general embedding of the general curve. We're just talking about the general point of GRD of U. And there's a number of open problems here, which are quite fundamental to the understanding of curves. And these have to do with understanding the geometry or the algebra of the general embedding. So what do I mean by that? Well, you could ask, for instance, what's the Hilbert function? What are the degrees and ranks of the syzygies? Okay, so just, for instance, one special case of this would be the case r equals g minus 1, d equals 2g minus 2. And then the prediction about the syzygies of the canonical embedding of the general curve is Green's conjecture. And then, so this is for the general curve. This is now a theorem of Voisin. The Hilbert function of the general embedding remains an open problem. And we have a predicted answer, which comes from the maximal rank conjecture. And so the statement of this conjecture is attributed to Max Noether, who worked on related questions in the 1870s. It was studied by many people classically. Severi wrote about it in his paper on unirationality of Mg for small g in 1915, so a century ago. And this was popularized by Joe Harris in the 1980s. And many, many people have worked on this. So I'm not trying to give any sort of comprehensive history here. And the statement is this. So if we have some linear series, and this gives a general embedding, and X is general, then there's a multiplication map which takes the nth symmetric power of the linear series V and maps to sections of the mth tensor power of the line bundle. And the conjecture is that this linear map has maximal rank, meaning that it's either injective or surjective. So I said that this conjecture predicts the Hilbert function of the general embedding, and so I should briefly explain why. So note that the kernel of mu m is the space of homogeneous polynomials of degree m that vanish on the image of the embedding of x in PR. So we're looking, so this is predicting the, right, so the dimension of the kernel is the dimension of a graded piece of the ideal sheaf. And then we need to know the dimensions of these two pieces. And the dimension of this piece is easy. So the dimension of sim mv is r plus m choose m. And the Petri condition plus the base point free pencil trick together imply that multiples of special divisors are non-special. So what that means here is that the dimension of gamma x L tensor m is equal to md minus g plus 1 for m at least 2. So saying that this has maximal rank tells us exactly what the dimension of the kernel is. So that tells us the dimension of that graded piece of the ideal sheaf, and hence predicts the Hilbert function. Yes. And if you fix G, D, and R, then you only have to check finitely many M. So, okay. So there's many partial results here. There's really a rich history of work on this problem, and even partial results have had significant applications. So, so partial results for all m, it's known when r is less than or equal to 3, or in the non-special case, so meaning that the rank is less than or equal to d minus g. So this is the case when the linear series can be incomplete, when the general linear series can be incomplete. And this is work of Balico and Elia from the 1980s. For m equals 2, there's the case of adjoints of gonality pencils. And this is work of Voisin from 1992. And this was a key technical result in the proof of surjectivity of wall maps. Other cases for m equals 2. So Teixidor proved a strong form of the conjecture for m equals 2 when d is less than g plus 2. So in fact, here she proved that the maximal rank condition holds not just for a general linear series, but for every linear series of this degree. So when d is less than g plus 2. So this is 2003. In 2009, Farkas proved the case where rho equals 0, and when mu m is when mu 2 is an isomorphism. So r plus 2 choose 2 is equal to 2d minus g plus 1. And this computation gives an infinite sequence of counterexamples to the slope conjecture. So even just doing individual cases of a conjecture like this has real consequences about the geometry of curves. And again, I should say this is far from comprehensive. There are many, many more partial results. In particular, there are many papers on this topic by Balico. And I'm not trying to give a comprehensive picture of everything that has been said on this conjecture. What I do want to talk about is how tropical methods can prove results in this direction. And And so I'm going to start with essentially the same graph that Matt Baker talked about in his lecture series. So the graph will be called gamma. And I've added a bridge at the left end and the right end. This does not do anything to the set of divisor classes or their rank, but these edges at the two ends show up in various arguments. So we label the vertices. So W0 is to the left of V1, and this is the same notation as in Matt's talk. So V1 and W1 are the left and right endpoints of the first loop, and so on until we get here to VG and WG, and VG plus 1 is the right endpoint of the graph. And I need to make some fairly strong assumptions on the edge lengths of this graph. So LK will be the length of the top edge on the kth loop. MK will be the length of the bottom edge. And NK will be the length of the bridge between the kth loop and the k plus first loop. And what we need to assume is that LK is much longer than MK. And NK is much longer than LK and also much longer than LK plus 1. So the bridges are very long. There's a big space in between adjacent loops. And finally, there's a condition that's really of quite different flavor from anything that's appeared in previous work in tropical Brill-Noether theory. And this is that there should be no linear relations among M1 through Mg with small integer coefficients. And here small means less than or equal to g plus 1. And with more care, I could be more precise about what these bounds should be. They're not too bad. N, the length of the bridge. M, yep. Okay, so this is our graph, and let me state the theorem. Which should be on the archive quite soon, so maybe in the next week or so. Okay, so let x be a curve with skeleton gamma over K algebraically closed. We'll assume that rho is at least 3, and we'll assume that we are in the special case, so meaning that the rank is greater than d minus g. So this means that the general linear series is complete, and we will only argue with complete linear series. Then there is a divisor dx of degree d and rank r on x, such that mu2 from sim2 of the complete linear series to the complete linear series of 2dx has maximal rank. From this, using classical techniques, we can also make statements about the higher multiplication maps when mu2 is surjective. So furthermore, if mu2 is surjective, which exactly means that r plus 2 choose 2 is greater than or equal to 2d minus g plus 1, then, and one more hypothesis, and the characteristic is 0, then mu m is surjective for all m. So this part of the statement is where tropical techniques come in. And deducing this from the surjectivity of mu2 is a classical exercise in the geometry of curves. It requires characteristic 0 because the argument uses the uniform position lemma. So the technique of the proof is the tropical independence that Matt Baker talked about in his lecture course.
So this combined with the work you mentioned about area shows m equals 2, that is true. Right?
Yes, so the maximal rank conjecture is true for quadrics. Right, so the reason why we say quadrics is that m equals 2 is a prediction about the space of quadrics that contain the general embedding of the general curve. So the maximal rank conjecture is true for quadrics. Okay, so the proof is going to be by tropical independence. R equals 0, 1, and 2. Those are the 4 cases that I erased. They're very easy. I'm sorry. Thank you. Yeah, r greater than or equal to 3. Sorry. Yeah. Okay. Okay, so step 1. So we want to be able to choose the tropical divisor that we work with. And in order to do this, we need to know that when we have a divisor of degree d and rank r on our graph, that there exists a divisor of degree d and rank r on our curve that tropicalizes to this one. And so this is the lifting step. So this is lifting. And this is a paper joint with Dustin Cartwright and Dave Jensen, which just appeared. So it was just printed. And so the statement here is let D be a divisor of degree D and rank R on gamma. Then there exists dx of rank R on x such that D is the tropicalization of dx. So in other words, the tropicalization map from WRD of x to WRD of gamma is surjective. And, well, okay, so in order to say that on the metric graph side, I should say that my valued field is maybe spherically complete and the valuation surjects onto the real numbers. But okay, otherwise, we have to say something about D being rational over the value group. But this is the D that I'm going to choose is going to be rational over the value group for whatever choice you want to make. I should say a few words about the proof of this lifting theorem. I should say there are 2 proofs. So there's a proof I understand from Amini and Baker that uses a 2-step degeneration. And there's a different argument that appears in this paper, which I'll explain. And so the proof was really inspired by tropical scheme theory. So we had a meeting at Yale a while back, and we were hearing all about these bend relations. And what we wanted to do was understand what WRD of gamma is as a tropical scheme. And in so doing, we understood how to lift. Gamma is always going to be that graph.
Right, because for general graphs, this is an extremely...
Oh, and completely false. Yeah. Okay, so throughout, this is gamma. X is always a curve with gamma as its skeleton. R is always at least 3. Rho of GRD is always non-negative. So those are going to be standing hypotheses for the whole talk.
Specific graph will provide a statement for general curves.
Correct. So that's what I was saying at the very beginning, that the universal GRD over the Bronner-de Peccei locus is irreducible. And all of these statements are about groups that are upper semi-continuous. And so once we have it for one curve and one linear series, then we have it for an open dense subset. Okay. The lifting requires that the bridges have non-zero length. No, let me take that back. Lifting does not require bridges. Gieseker-Petri requires bridges to have non-zero length, and maximal rank for quadrics requires the bridges to be long. So, okay. So let's see, lifting. So we use the Baker-Noreen definition of rank to express WRD of gamma as an intersection of translates of theta. So the theta divisor on the Jacobian or on pic D. Okay. I guess I should say pic G minus 1. But just choose a base point. Okay. And we're expressing WRD of gamma as an intersection of translates of theta. And then there's something to check on the algebraic geometry side, which is to check that WRD of x is scheme theoretically a corresponding intersection of translates of the theta divisor on the Jacobian of x. So now we have a correspondence between these two pictures, and we need to use the fact that the skeleton of the Jacobian of x is the Jacobian of gamma. And this is an important technical fact that is due to Matt Baker and Joe Rabinoff. And now I should say that WRD is not a local complete intersection. It is a degeneracy locus. It's not a local complete intersection. But on an open dense subset, it's smooth. And so on that open dense subset, away from WR plus 1D, we can realize it as an intersection of codimension many. So R plus 1 times G minus D plus R translates of theta. And these vertex avoiding divisor classes live in that locus. So let me say that. So near a vertex avoiding class, WRD of gamma is an intersection of R plus 1 times G minus D plus R translates. And then we're locally in a complete intersection case where we can apply nice lifting theorems.
In my talks, I think I just called those generic. I didn't use the term vertex avoiding.
Okay, so what Matt called generic, we've always been calling vertex avoiding. It has a very specific definition. So it's not just some open set. It's a very specific open set. And, okay. And now what did I want to say here? Okay, and so then use lifting theorems for complete intersections. So there were algebraic versions of these lifting theorems that I worked on with Brian Osserman, but these aren't enough for this particular lifting. We actually have to work locally analytically, and Joe Rabinoff, in his thesis, proved the analytic version that we need. And so now what we're doing is we say, well, locally near this point, we have a complete intersection, and then we intersect with rho more translates of theta to get a finite set. That allows us to show that this point lifts with a predicted multiplicity into that complete intersection, which has the wrong dimension. But in particular, it lifts with at most that multiplicity into WRD of gamma, and then we do some counting argument to show that it must be a bijection. Okay. The upshot of the lifting result is that we can choose our favorite tropical divisor to work with. So of course, we're going to choose it to be vertex avoiding. And so for simplicity, I'm only going to talk about the case rho of GRD equals 0. So I should say this is really the crucial case. So there's even a theorem of G. Wang that was published just this year, which says that the maximal rank conjecture for m equals 2 and rho of GRD equals 0 implies the maximal rank conjecture for m equals 2. So if you like, you can prove the maximal rank conjecture for m equals 2 in the rho equals 0 case, and then deduce it in this higher case. But we actually give a tropical independence proof for all rho. So our argument does not depend on this reduction, but I just want to emphasize that rho equals 0 is the crucial case. So rho equals 0 means that G is equal to R plus 1 times G minus D plus R. And because G minus D plus R appears everywhere, we call it S. So if you're thinking in terms of algebraic geometry, R plus 1 is H0 of the line bundle, G minus D plus R is H1, or it's H0 of the adjoint. Okay, so this is some very natural number that sort of course, has to appear everywhere. And now we have to choose a What's that? S is H1, R plus 1 is H0. Yep, and so now we're going to make a tableau. It's going to have R plus 1 columns and S rows. So there are a few canonical choices that one could make. And the choice that we make is 1, 2, 3, S, S plus 1, 2S, and so on. So here we have G and G minus S plus 1, G minus S plus 2. Okay. So that's the tableau that we're going to use. Okay, so D is going to be W0 reduced. So remember, W0 is the left endpoint and corresponding to this tableau. And maybe I should say when rho is 0, all divisors are vertex avoiding. So that's part of what makes rho equals 0 so much easier to work with. And now I want to remind you of some facts from Matt's lecture. So recall, from Baker's lectures or from the tropical proof of the Brill-Noether theorem, that for 0 less than or equal to I less than or equal to R, there exists a unique di, which is equivalent to d, such that so there exists a unique effective di equivalent to d such that the degree at W0 of di is equal to I, and the degree at Vg plus 1 of di is equal to R minus I. And we understand, so that means, so then we can choose psi I, giving this equivalence. So choose psi I such that di is equal to d plus the divisor of psi I. And then this psi I, so it's uniquely determined up to an additive constant, and it's completely understood. So in other words, in terms of the combinatorics of the tableau, we know the slope of psi I on every bridge. We know the slope of psi I on every bottom edge. So it's constant slope on bridges and bottom edges. It bends on the top edges, and we know exactly where it bends and what its slopes are on each of the regions. So these are very explicit functions, and we can work with them very, very precisely, and we do. Okay, so as I said before, the dimension of sim2 is r plus 2 choose 2. The dimension of L of 2dx is 2d minus g plus 1. And so, okay, so that tells us what we want the rank of the map to be. It should be the minimum of those two. And so for 0 less than or equal to I less than or equal to j less than or equal to r, let psi ij equal psi I plus psi j. And, and as Matt mentioned in his talk, there exists fi in the linear series on the curve upstairs such that the tropicalization of fi is equal to psi I. And that follows from the uniqueness of di. So now we've lifted this to an actual function in the actual algebraic linear series. And you note that psi I plus psi j is the tropicalization of mu2 applied to fi tensor fj, or the image of fi tensor fj in the symmetric square. And so that means that we have these rational functions, fi times fj, which live in the image of mu2. And if we can find enough of them that are tropically independent, then that gives us, so when we have some collection that's tropically independent, that gives us a lower bound on the rank of mu2. So the tropical statement that we prove is that there is a subset A in the set of pairs, so 0 less than or equal to, so the set of I, j integer points, such that 0 is less than or equal to I, less than or equal to j, less than or equal to r. And this set has the desired size, which is the minimum of r plus 2 choose 2 and 2d minus g plus 1, according to whether mu2 should be injective or surjective, such that the set of psi ij such that ij is in A is tropically independent. This set A is far from unique. So when we're in the surjective case, which is the 2d minus g plus 1 case, and we actually have to choose A, there are many choices. And finding a consistent way of making the choices is actually a headache. The theorem would be easier to prove if the choice of A were canonical. But so in some sense, the theorem is more true in the sense that there are many, many choices you could make for A, but that non-canonicity WRD is globally an intersection of translates of theta, many, many more translates than the codimension.
The word locally should be on the board,
No, this is globally an intersection of translates of theta, but the number of translates is much greater than the codimension. So it is not a complete intersection of translates of theta, it is an intersection of translates of theta. Okay. So we conjecture that this type of tropical independence structure will hold for higher degrees. And so here's the conjecture. So if R is at least 3, rho of GRD is at least 0, and R is less than D minus G, then there is a chain of loops with generic edge length, so sufficiently general for the Petri condition to hold. And the vertex avoiding divisor D of degree D and rank R with some set A with a collection of multisets I of integers from 0 to R. And the size of this set A should be the size required for maximal rank to hold, which is the minimum of R plus M choose M and MD minus G plus 1. Such that the corresponding collection of piecewise linear functions, so the set of sum I, the sum over I in I psi I, such that big I is in this collection A, is tropically independent. So for each fixed G, R, D, and M, this conjecture implies the maximal rank conjecture for the same G, R, D, and M. So we prove this conjecture for M equals 2, and we also prove the conjecture for MD less than 2G plus 4. So this is a partial generalization of the results of Teixeidor, which was for M equals 2 and D less than G plus 2. It's only a partial generalization because our result is weaker. We're only giving the existence of a divisor, whereas when D is less than G plus 2, Teixeidor proves that every linear series satisfies the maximal rank conjecture, or satisfies the maximal rank condition. Okay, so now I should start explaining how does one go about proving this sort of tropical independence statement. Yes?
Just to summarize again some things I think Edwin didn't write down so it's clear. This is a purely combinatorial conjecture, right?
Yes.
About existence of certain graphs with certain divisors and a certain set A.
Correct.
That's combinatorial conjecture is true, then the maximal rank conjecture is true for all M.
Correct. Yep. Right. And I should say that sort of case by case, if you fix G, R, D, and M relatively small, you can typically verify the conjecture. So on the other hand, sort of finding a coherent algorithm for constructing the set A and proving the tropical independence seems to be a delicate matter. So, okay. All right, so let's start with the easy case. So maybe I should also say, so we proved the conjecture for m equals 1. So let's do the conjecture for m equals 1. And here again, you're going to see that not only is the conjecture true, but it's very, very true. Okay, so what do I mean by that? Okay, so on every edge, each psi I has constant slope. And these slopes are distinct. So suppose you can add constants to each of these functions so that the minimum occurs everywhere at least twice. Then on every edge, there have to be two functions that have the same slope. So you could look at any of, you could look at on every bridge, or you could take bottom edge. Each psi I has constant slope, and these slopes are distinct. So you could take any of those edges and find a proof that these are tropically independent. So choose whichever bridge you want, and you have tropical independence. Okay. So now let's start making steps towards the proof for m equals 2. So we're going to let small theta be the minimum of the psi ij's. And we have an associated effective divisor in the linear system of 2D, which is 2D plus div theta. So if the minimum occurs twice, at every point on that left-hand bridge that I added, so W0 to V1, then the degree at W0 of delta is at least 2. So this is the same argument. So the degree of delta can be read off from the slope of theta, which has to agree with the slope of two psi ij's. And there's one psi ij, which gives the slope that would give degree 0. That's psi 0, 0. And psi 0, 1 is the only psi ij that gives the slope that would give the degree 1. So because there are at least two psi ij's that achieve the minimum on this edge, the degree has to be at least 2. So similarly, if min occurs twice on the last bridge, so from WG to VG plus 1, then the degree at VG plus 1 of delta is at least 2. So we split our graph up into locally closed pieces. So each with one loop except for the bridges on the ends. So gamma k is the segment that contains the kth loop. So here we have gamma 0, and here we have gamma g plus 1. And what we've shown so far is that if there's a tropical dependence, the minimum occurs twice everywhere, then the degree on gamma 0 is at least 2, and the degree on gamma g plus 1 is at least 2. And now I want to argue that the degree on each gamma k is at least 2. So let me explain why that's true. Okay, so here's an observation. There exists a unique I such that the degree of di restricted to gamma k, so for each k, there exists a unique I such that the degree of di restricted to gamma k is 0. All dj for j not equal to I contain distinct points on gamma k. So you can distinguish all these di's by looking at any given loop. So as a consequence, if I is not equal to j, then there does not exist any constant b such that psi ij plus b is equal to psi I prime j prime. So if you're trying to get the minimum to occur twice on one loop, you have to have at least 3 psi ij's involved. You can't just have 2 that agree on the whole loop. Okay, so now you have 3 involved, and one of them does not attain the minimum on the entire loop. So if the minimum occurs twice on the kth loop, then there exists ij, and we can actually make this happen on the loop, not on the bridges. So then there exists ij such that psi ij achieves the minimum on some, but not all, of the kth loop. And then there's a lemma which appeared already in the Gieseker-Petri paper, which says that the boundary points of the set of V such that psi ij of V achieves the minimum are contained in delta. And so now, since we have some psi ij that achieves the minimum on some but not all of the loop, then the locus where it attains the minimum has at least 2 boundary points. And those boundary points must be contained in delta. Okay. Okay, so that implies that the degree of delta restricted to gamma k is at least 2. So again, assuming that the minimum occurs twice. So as a corollary, the conjecture is true for 2d less than 2g plus 4. And the same argument works for md less than 2g plus 4. I won't go through the details. So let me conclude with an example that shows you the wrinkle where the linear relations among edge lengths occur. So what do we do when 2d is greater than or equal to 2g plus 4? Then we need some other argument. So we need to show that this delta would have more points somewhere else, or something else would happen. So here's the example that I'd like to give you. So this is g equals 10, r equals 4, d equals 12. And so this is a case of an adjoint of a gonality pencil. So this is the case that was studied by Voisin. This is actually exactly the case that leads to the first counter example to the slope conjecture. So this is in the work of Farkas and Popa from 2005. And what's happening here is that because the maximal rank conjecture is true for m equals 2 in this case, then you can compute so then there's a closed set where the maximal rank condition fails, and you can compute that closed set has to have pure codimension 1. And then because you've realized it as a degeneracy locus through the maximal rank conjecture, you can compute its cohomology class. And knowing its cohomology class is, so then you compute the slope of that class, and you get a counterexample to the slope conjecture. So even a specific case like this is a statement that has real geometric meaning and real geometric consequences. And so r plus 1 is 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now notice that 2d is equal to 2g plus 4 is equal to 24. Okay, so assume that the minimum occurs everywhere twice. That implies that the degree of delta restricted to gamma I is equal to 2 for all I. Now, the important thing here is if I know the degree of delta to the left of some point on the graph, say on a bridge, then I know the slope of theta on that bridge. And knowing the slope of, and these bridges are really long. So if you have the wrong slope on one of these bridges, then the value of your function gets way off. So let me draw a schematic diagram. So let's say that so theta looks like whatever it looks like. And now we have some psi ij. And because these bridges are very long, okay, so say I'm achieving the minimum somewhere on the kth loop, the slope has to be coming down from the left and going up to the right. And then once it's achieved the minimum for a while, once the slope is wrong, it will be wrong forever. So it won't reappear on the next loop. So in other words, by knowing the degree on each loop, then you know the slope of theta on every bridge. And because the bridges are very long, that gives you restrictions on which psi ij can attain the minimum on each loop. And so then when you look at what those restrictions are, you then zoom in on the middle of the graph, the 5th and the 6th loops. So let me draw a picture. So I'll finish with this picture. So you get to, so here's gamma 5 and here's gamma 6. And there's only one combinatorial possibility for which functions can achieve the minimum on which regions. And it's psi 1, 3 and psi 0, 4 achieve the minimum on this bridge, on both bottom edges, and on these two bridges. So, so these are the 2 points of delta on this loop. And between the 2 points of delta, it's psi 2, 2 and psi 1, 3. And between the 2 points of delta on the top of the 6th loop, it's again psi 2, 2 and psi 1, 3. Now, in between these 2 points of delta, there's a point of D, of the original divisor that we started with. And what we're going to do is evaluate psi 2, 2 and psi 1, 3 at these 2 points. So we know the slope of psi 2, 2 everywhere. So in particular, even though psi 2, 2 is only defined up to an additive constant, we know explicitly what psi22 at this point minus psi22 at this point is. Okay, so psi22, so let's call this x6 and call this x5. Psi22 of x6 minus psi22 of x5 is an explicit linear combination of edge lengths. So and here it's just mk and nk that appear. So it's actually m5, m6, and n5. And we could do the same for psi13 of x6 minus psi13 of x5. But if psi22 agrees with psi13 at this point and at this point, then we can subtract these two, and we have to get 0. So this implies that an explicit linear combination of m5, m6, and n5 is equal to 0. And when you do the computation, which I'm not going to do here, you actually get that m5 is equal to m6. Okay, so it's a linear relation with small integer coefficients. But our assumption on the graph, we chose the graph so that this is not true. Okay? So again, we assumed that there was a tropical dependence. We produced a small linear relation among the edge lengths, and we conclude that there's no tropical dependence. Okay, I'll stop there.